This video will explain the strategy known as Universal Formula Reductio variant, and will show how to use it in the context of a proof. So suppose that we want to derive a universal formula. Let's say a formula of the form for all x, if px, then qx. So how are we going to do that in our system? So you would think that we would use some rule, something like universal quantifier in, given the way our rule set has been set up so far with an in rule and an out rule for each operator. After all, we have the rule of universal quantifier out and existential quantifier out and existential quantifier in, so why not universal quantifier in? So we could have a rule like this, but it turns out that, so like the rule of E out, which has a restriction, the rule of universal quantifier in would also have restrictions. It would have even more complicated restrictions than the restrictions that we have on existential out. So to avoid those complications, we're not going to have a rule of universal quantifier in. Instead, every time we want to derive a universal formula, we're going to get it via reductio. So, how that will work is like this. So we want to derive a universal statement. So we're going to do that by assuming the opposite of this statement. It's false that for all x, if px, then qx, as a provisional assumption. And then, through a series of steps, we're going to try to get a contradiction. And then if we are able to do that, then we can derive for all x, if px, then qx, by the rule of not out. So let's say that our provisional assumption is on line A. Of course, there are some premises or derived lines above it, A, that we're not seeing. They're not relevant for this sketch of the proof. So, but then we encounter a problem on line A, which is that we have a negated universal statement on line A. And we can't use any of the rules that I've already discussed. In particular, we can't use the rule of universal out on line A because of the negation in front of the universal quantifier. So we need to get rid of that negation in the front. We need to move it somewhere else. So we will use a rule called QE, and it does precisely that. What the rule of QE does is it moves the negation, it switches the quantifier. So the quantifier will switch from universal to existential, or vice versa. If we have a negated existential, it'll switch to a universal quantifier. And then the negation moves to the other side of the quantifier. And then we just keep the rest of the statement as it is. So that's how the rule of QE works. So we'll cite line A and the rule of QE. Okay, so now we can instantiate line B. So we're going to instantiate it with the letter A. Let's assume, for the sake of argument, that A does not appear anywhere else in the proof. So that will be by line B and the rule of existential out. And of course, since we're doing existential out, we need to flag the letter we used to instantiate. So we'll flag A. So now we have a negated conditional on line C. And that's likewise a problem because we can't do a whole lot with that negated conditional. We can't use any of our rules for conditional on it. So we're going to want to do one more thing. And that is to convert this to something that's a little easier to deal with. So we'll convert it to PA, and it's false that QA by the rule of arrow, which is abbreviated AR. So that's the sequence of steps that you're going to go through every time you want to prove a universal statement. So every time you want to prove a universal statement, you're just going to, boom, automatically assume the opposite of the negation of that statement. Then you're going to use QE to push that negation in to get an existential with a negated statement inside, embedded under the existential quantifier. And then when you instantiate that existential statement, you get a negated conditional, then you're going to want to use the rule of arrow to break that down and make that something easier to deal with. That's not going to happen necessarily every time because you can have universal statements that have other operators embedded under the quantifier, or have no operators because you could have a statement for all x, px. So you wouldn't need to do the arrow step necessarily every time, but you're going to do it a lot of the time. Okay, so now that you have a basic sketch of how this strategy works and the different steps that we're going to do, let's look at this in the context of a proof. So recall the penguin argument from the first day of class. Everything that flies is a bird. Penguins can fly. Therefore, penguins are birds. So we're now in a position to do a proof of this argument. So our first premise is everything that flies is a bird. So we're going to say for all x, so the first line line 1 is going to say for all x, if x flies, then x is a bird. Our second premise will be line 2, and that says all penguins can fly. So again, we're going to need a for all x. If x is a penguin, then x can fly. Sorry, that should be capital. X can fly. And our conclusion then is for all, so our conclusion is penguins are birds. So we have the statement for all x, if x is a penguin, then x is a bird. Okay, so since we want to prove a universal statement, I'll put that down at the bottom, and we're going to assume the opposite of that on line 3. So we'll assume it's false that all penguins are birds. That's a provisional assumption. Then we need to do QE on it. So we'll get there exists an x such that it's false that if px, then bx. And that's by line 3 and the rule of QE. Okay. Now we can instantiate that line, do existential out on it, and so we'll get it's false that, and we're going to use the letter A because A does not already appear in the proof, so we can use A. And that's by 4 existential out. Okay, and then we can then we want to do the rule of arrow, so this will also depend on line 3. So we'll get PA and it's false that BA by 5 AR. Okay, now it's time to instantiate our universal formulas on lines 1 and 2. So we'll get FA arrow BA, and we'll get PA arrow FA. So the first of these is by 1 universal out, and the second is by 2 universal out. Then on line 9, we want to take out PA from line 6. That's by 6 and out. And now that we have PA, we can use that to get FA out of line 8. So that'll depend on 2 and 3. That'll be by 8, 9, arrow out. And once we have FA, we can get BA out of line 7. So our next line will depend on 1, 2, and 3. That's line 11. We can get BA by 7, 10, arrow out. And once we have BA, now we can also get not BA from line 6. So that'll depend on 3. Not BA by 6 and out. And then we have what we need for a contradiction. So line 13 will depend on 1, 2, and 3. And that will be BA and not BA by 11, 12, and in. And we have our contradiction, so now we can get our conclusion. That will depend on 1 and 2. And we will get for every x, if px, then bx by 3 through 13, not out. And that concludes our proof. We would still need to put a box on this, so you can draw a box in here. So something like that. And so that's how you do a universal formula, how you prove a universal formula in our system.